Mic check. Hello everyone. I heard that today we got at least one person who doesn't speak Czech, so we just start like that. Welcome to yet another edition of Pyvo. Surprisingly, before Easter. Okay, that wasn't surprising. What is surprising though is that so many of you came here today, despite of the date and of the weather. But come on, we've got the best speakers here, so obviously where else would you go? Anyway, so today we are going to hear a lot about interesting things around microscopes and processing data, so hey, it's going to be fun. Bit of organizational details. If you need a drink, maybe you have last chance, with 2 minutes to go. We will have a lightning talk today, as far as I'm aware, most likely, probably. We will do it right after the end of presentations. Questions, how would you like to have a question?
During the presentation, I want to make it like highly interactive.
Yeah, from us to you, from you to us.
Asking you as well.
To him, not to us. I'll be just sitting there and recording. And after the lightning talk, networking, go grab more beers, and then let's talk Python and have fun. Welcome Lukáš, today's speaker. He's my upstairs neighbor, so that's why we have him today. It's very hard to find out.
That's actually the reason why I'm here, because I feel somehow obliged to Jakub, because I've got 3 sons, and they are not the quietest one in the world, and I still think and I believe like we are making hell out of his life, but he's constantly telling me not. But so that's why I'm here. And he's a very nice guy, because the previous tenant called the municipal police on us.
I didn't.
Yeah. So that's why I'm here. So I hope for maybe another month. You can
right. So and then after a few months we will repeat with different topics.
We already discussed some topics on the way there.
And this is a segue to a little advertisement that we are always looking for speakers. So if you make a noise at home, or just want to try be a speaker, then just tell us and come up with some any topic really around Python, and you can try your stage here. We call it really unconsequential talk, because what happens here usually stays here. Okay, we record it, we put it on YouTube, but come on, your employer doesn't need to know about it. I'm still employed, so I guess it's fine.
That's why I choose not to use my company template and completely record the presentation. It was exactly.
We have
proprietary and confidential.
Okay, so welcome and big hand to Lukáš. I think we can start.
So hi everyone, as I said, I want to make this highly interactive. So I will start anyone with some background in image processing, computer vision, anyone using OpenCV, stuff like that, scikit image, great. So now I'm not very comfortable with Okay. So I will be talking about some image analysis and how we are using it for automation of our electron microscopes. I'm using electron microscope. I came here from Thermo Fisher Scientific. If you don't know us, we are probably the largest producer of electron microscope worldwide. Here in Brno, we've got largest factory in the world for scanning electron microscopes and transmission electron microscopes. And I'm leading software development for automation of the systems using some image processing, computer vision, making the images nicer to use full potential of our hardware, or improving ease of use with the microscope. So I will start with something about scanning electron microscope. To know any differences between light microscope and electron microscope?
Sorry, good.
Like if you are aware, like what can be differences between light microscope and scanning electron microscope, or in general?
Light microscopes have light as the viewing substance, or photons as the viewing particles, and electron microscopes electrons. So they have shorter wavelengths, so they have a better resolution.
Exactly. But they have like some common stuff actually. Like as you said, we are using electrons instead of photons. But we also have lenses. These are not like glass lenses as in conventional light microscope, but it can be like magnetic or electrostatic lenses. And we also have like some optical imperfections, which will be correcting in this presentation. So the basis of the scanning electron microscope, as I said, the differences between scanning electron microscope and transmission electron microscope is that in the scanning electron microscope, the beam is scanning the sample, and then there are like electrons emitted from the sample, which we are gathering using various detectors. In the transmission microscope, the electron beam goes through the sample, and there's like nowadays camera in the bottom of the TEM, transmission electron microscope. But I'm coming from this SEM part, so I will be talking about SEMs. Or maybe where's the laser pointer? Here. Well, can you help me, guys?
Laser pointer.
We got some source of the electrons. It can be like some tungsten filament, or it can be what we call field emission gun and different stuff. Then there's extraction cathode, which is setting the energy of the electrons. So with the higher energy, the electrons will penetrate deeper into the sample. But also, since you've got a larger interaction volume, then you are somehow losing some resolution. Then there are like, for example, aperture. Aperture is setting the current of the beam. So higher current gives you larger path of the beam and thus larger signal to noise ratio, but also reduces your resolution. So ultimately, we want to use lower accelerating voltage and lower beam current to get the image with the best possible resolution, but such images are very noisy. If you are wondering what's the resolution of SEMs, it's around 1 nanometer. With the TEMs is 1 angstrom, like 0.1 nanometer. So with the TEM, we are able to actually see the atomic lattice of the sample. And then there are like some scanning coils, and obviously the sample. We will be also talking about something called working distance. Working distance is the distance between the sample and here is like something called the pole piece. Then when the sample hits, when the beam hits the sample, there can be, like in general, there can be more types of interaction, but now we are considering just this three of those. Either the primary electron can hit the secondary electron, and which exits the atom, and then this is the secondary electron, which has like very low energy, and these electrons usually brings us the actual resolution and the surface of the sample. Then this is called like inelastic scattering. During the elastic scattering, we've got backscatter electron, which has like energy quite similar to the primary beam. and this usually brings us information about the composition of the sample, like a chemical composition. And to get the actual chemical composition, we can use X-ray detectors, because you probably remember it from chemistry. When we hit some electron, or when the electron exits some inner shell of the atom, it's in excitated state, and during the de-excitation it emits the characteristic X-ray, and this X-ray energy is characteristic for each chemical sample. So we can make a chemical composition, or detect the chemical composition of the sample. So that's it. Back to the image processing, Python, OpenCV stuff. I will be using several images. Actually, I'm reusing this presentation from, I don't know, 5 years ago, when this thermoscientific SIOS 2 was just released. This is the mid-range dual beam microscope. What I mean by dual beam, the single beam microscope has just one column, which uses the electron for getting the signal. But this is the dual beam, so we have also another beam called focus ion beam, which is using ions, mostly from the gallium. And with this, you can actually dig into the sample, because the ions are have much larger mass than electrons, and thus you can mill into the sample. And we are using this technology to prepare so-called lamellas, which goes into the transmission electron microscope, because there is a requirement for the sample to be just tens of nanometers thick. This is our, I would say, testing sample. We like thin balls on carbon. We like it for the image processing, because it has edges in all the directions and produce a good signal. And I was talking about the current, high voltage. This is what we use. One of the important aspects when you are acquiring your images is this called this dwell time. So this is the time amount, or how long the beam stays on each of the pixels. So the higher the dwell time, the better signal to noise ratio, but also there can be some sample damage. For example, we have some nanoparticles samples which you will just scan once and then they will melt. So you have to be cautious to somehow balance your dwell time and what the beam can handle. And this is probably it. So we will start with the first assignment. Which image do you prefer out of these three? Which has the middle one. So maybe we can vote. First one, second one, great. Third one, good. So how to? So what would you? How would you estimate which of the images is the best? I'm talking here about the contrast and brightness. This is actually this doesn't have anything to do with the column, but with the detectors. The contrast is set by the gain of the detector, and brightness is set by the offset of the detector. And we need to find the optimal settings to get an image which is not very dark or bright. So yeah, any ideas what to look for?
Maybe maximize the standard deviation of the histogram.
Yeah, that's great. Yeah, and what's the histogram?
Histogram is a bin of each value of the pixels. How many pixels are with each value.
Great. Yeah, exactly. So these are the histograms of each of the images. And as you see, the images you like the most has like maybe call it like equally distributed values in the histogram. So we will be looking for it. And as you exactly describe, I don't need to describe the histogram anymore. So let's dive into the code. And yeah. So I have here presented some, prepared some Jupyter notebooks. These are my images with set like a combination of different contrast and brightness. So I can go through it and let's find the optimal settings. Yeah, so I'm importing the modules. As I said, like most important is like OpenCV. Anyone have like some experience with the OpenCV, like maybe from the university or whatsoever? Great. We use the OpenCV because like mostly it's like I would say industry standard. I think it began in the Intel, and the good thing is that we can develop these prototypes within the Python and then just rewrote them in, for example, into the C++ or C#, because OpenCV has like wrappers for many languages, including Rust. But I haven't tried it yet. So yeah, let's read the images. And yeah, I have like this support function. And exactly as you said, one of the metric I can look for is like standard deviation of the image. And I also included two others because as I showed, I also want to have the histogram somewhere in the middle mostly. So I also included measurement on how far is it from the middle of the histogram, and I also don't want to have like many what we call like clipped values. This is the values because now we are using 8-bit images, and clip values are like either 0 or 255. So I want to also reduce this, and so I'm minimizing the amount of the clip values, minimizing the distance from the mean, and maximizing the standard deviation, which is being done here. And then I just normalize those values and sum it to get some score. And yeah, this is how we got the image. Then I have like I had like another idea. Everything is same, but do you know how the ideal histogram should look like?
Gauss?
Sorry?
Gauss?
Yeah, but yeah, it might be a Gauss, but ideal what the photographers are trying to achieve like is to have like a flat histogram, and this is what I wanted to achieve. So I somehow simulated the ideal histogram by this method, and then calculate the actual histogram of the image. And again, I'm trying to minimize the differences of those. And yeah, I've got that was 80, this was 78. If we would look over here, yeah, this one or either this one. I like this one more. Cool. So that was contrast and brightness. Actually, we call these functions auto functions. So the user doesn't need to manually align those values, but he just hits one button and find those values, the optimal conditions. Now let's get to the.
Sorry,
Go on.
does the microscope like image the sample multiple times with different values of this?
We also have like another method that we have like models of the detectors, and we are using those just to have one image and know, like see its histogram. We know how we want the histogram to look like, and then we just adjust just these two parameters and hopefully get the right image. Then let's talk about the focus. Obviously, we want to have like the in-focus image. Let's see the focus series I prepared here. So this is the images I have, and I want to find the most focused one. Any ideas?
Right. So
Yeah.
Laplace filter.
Uh-huh.
Laplace.
Yeah, Laplacian filter, good. Another ideas? I'm giving like this question during the interviews, so and it's like it's great. Like people are coming with various ideas. So one of the method we will get to the Laplacian, but I wanted to show you something more.
Wavelet.
Our wavelets are also good, yeah, but they are not in OpenCV. It sucks.
Is this called Fourier?
Yeah, this is the Fourier transform. Maybe you can tell us more about what we are seeing in the Fourier transform.
So I guess so like in the I can't remember if in the middle are the longest waves or
Yeah,
side
exactly.
waves.
Yeah.
And then in the corners are the shortest ones. And basically, you decompose the image into sine and cosine waves.
Yeah.
Different wavelengths, and the brightness is the amplitude of the.
Exactly.
Hired.
Yeah. But aren't you working for us already?
Yeah. I'm actually working for
it might be also competition. Yeah, because I don't know if you are familiar with that. Like Brno is like the Mecca or main city of the electron microscopy. We are like I don't have like no one give me strong data, but we are everywhere saying that 30% of worldwide production of electron microscope is coming from Brno. And besides Thermo Fisher, there are like two major companies, Tescan and DeLong Instruments, because they have like a common history in Tesla, not the Tesla we want to write, but different Tesla, technicky slabé, but no, it's ours. But yeah, Brno has like a great history of the electron microscopy. It's sad that I have this presentation just the week after this Dny elektronové microscopy happened. So yeah, it's a like good heritage, good genius. Yeah, I like it. So the frequency spectrum, actually when you perform the Fourier transform, you will get like the amplitude and phase spectrum. Here we are using just the amplitude spectrum, and exactly as you said, in the middle we've got the lower frequencies, and going to the borders of the spectrum we got higher frequencies. So now we can see that the image, which is more blurry, so it has like it doesn't have large frequencies, because you need those frequencies to give you edges and stuff like that. So it's like its energy is like around the center. And when we get the image which is sharp, has like many edges, it's like going to the edges, you've got larger values. So we will be using this as a metric in another task. So again, reading the images. and this is how we are calculating the magnitude spectrum. And when you weren't sure where are the high and low frequencies, because initially like even the, I believe MATLAB and stuff like that will give you the completely opposite, that the highest frequencies are in the corner of the result you get, but we are using this FFT shift and we just shift the quadrants to get the low frequencies to the middle. And you know, I need to also apply some logarithm because it's like super large values. And I will be just making sum for each of the image. We can also no compiler, thank you. So we see where is the sharpest image is supposed to be number 8. So let's see, yeah, number 8, going back to the data. Yeah, I think we agree that it's number 8. Let's try another method based on the Laplacian, I don't know. So yeah, we can actually quantify how many edges are in the image. So since the sharpest image has like multiple edges, so we can either use this Sobel or Laplacian operator. So we use let's use this one, and I'm just summing the absolute values of what I found. Maybe we can, let's try. Let's see edges, how the edges representation look like. Oh, it sucked, sorry. Yeah, I didn't prepare that, yeah, so, sorry. Then, yeah, we'll just again find the highest value, and it's again image number 8. Now let's try some more creative way how to find the sharpest image. So I showed and you mentioned the wavelets.
Yes.
Is somebody familiar with the JPEG?
What is it?
So you know the JPEG format for photos?
Discrete cosines.
Yeah, exactly. So JPEG is using discrete cosine transformation. Anyone familiar with the JPEG 2000?
It didn't get shown.
A lot, yeah. But this is using the wavelet transform. But I'm actually not familiar with, like, there's currently JPEG XL or something like that, but I'm not sure what's behind. So let's use the fact that, you know, when you have like sharper image, you have like more data in there, and to be able to encode them in the discrete cosine transformation, you need larger, you know, memory. So let's store these images not as pink, do they call it pink, right? But as JPEG. And now if you check like the sizes of the images, you see it's like proportional to how sharp it is. So if I go to the largest file, it's the most focused one. But I don't know if it's very effective to save each of the image to the hard drive and check its size. But that's it. Then, as I said, maybe, I don't know how many of us have glasses here, so if anyone has astigmatism, or I don't know if it's private, like, sorry, so I have astigmatism. So we have also astigmatism in our microscope, because imagine that you want to have like, as I said, like 1 nanometer resolution, but you are not able to create mechanically something with the 1 nanometer precision. So this is why we need those, we call it alignments, to get the beam into the center of the column, to correct the astigmatism. And this is what we are going to do. So I believe, like from physics, the definition of the astigmatic lens is it has like a different dimension in each axis. So this is how it looks like. So if you are over focused, you've got like this. I would call it like a line sharpness in one direction. Then if you go through the focus area, it doesn't produce the like a point, but it has like it's like a circle, and then it's like 90 degrees rotated. So what do you think? Which of the images is the least astigmatism? Yeah. So actually, this is what I was saying. Like all of them have astigmatism inside. So this is the overfocus. So I have like the astigmatism in this direction. Then when I should be in focus, I've got still blurry image because of the astigmatism. And when I'm under focus, it's 90 degrees rotated. So any idea what to use here?
Middle.
Sorry?
Middle.
Yeah, middle. And how to assign which one doesn't have like in a directionality inside.
Maybe we should try gradient in different directions,
Mhm.
but it would function because they're balls, but if
Yeah.
the sample would have like distinctive edges in one direction, then this approach.
Yeah, on
probably
distinct balls it will work, but we have like exactly as you're saying. So if the astigmatism would be in the same direction as some feature in the image, then we wouldn't be. You can't like distinguish by naked eye, so it doesn't. It actually fails with the software. So this is the good idea to have apply, for example, Sobel operator in both directions and calculate the angle. We will. Maybe next time I should try that. But we will again use the Fourier transform to detect the directionality in the image. Yeah, sorry, let's go here. This one. So.
How does one evaluate the directionality here? Because there were like huge crosses on the 0 and 90 degrees,
Mm-hmm.
and the off-axis ones weren't so pronounced.
So this is the series. Sorry, can you repeat the question?
Yeah. So in the Fourier transform,
Mm-hmm.
there were like crosses in the 0 and 90 degrees.
Yeah, yeah.
And the ones on the off-axis ones weren't so pronounced.
Yeah.
So I don't know how.
That's a good thing because when I was creating these images, the crosses you saw, this is caused by the edges of the image because there's like abrupt change. So you need to you see it in the spectrum.
Mhm.
If you would apply something called Hennig window, so it will be something similar to the Gaussian. So we will multiply it by some Gaussian. So we would have like dark borders. Then we wouldn't see those crosses. Yeah. For example, let's use. Yeah. So this is it. Now we see that the sharpness like in this direction. So I would have larger frequencies. The edges are more abrupt, perpendicular to the sharpness. So I would have the Fourier spectrum like more prominent values like in this direction, because I need to represent edges here. So the metric we will use here, and this is not we are using, is that I would just divide the spectrum into the 4 quadrants, and I need to find the image where you know, the sums are somehow like comparable. So if I have like astigmatism image, I have like large values in this direction and low in this one. So this is what I will use, and now I got the image in the middle. One of the interesting stuff is, for example, if we have like astigmatism image, it's very hard to focus on it, because as we saw here, this is like somehow more focused than this one. So we can try our metric for this, just for the different data. So you see that now I've got like 2 peaks, and actually the focused image should be like in the middle, just between those line focuses. Yeah, that was astigmatism. Now I was talking about the sampled image. The other phenomena we are observing is sample charging. So when you are hit, for example, if you have like some insulated samples, or usually biological samples, when they are like not properly grounded, what is usually being done if you want to put the bug or something like that into the scanning electron microscope, we will coat it with the, for example, gold or platina to get the charge, you know, back to the stage. So. And one of the methods for mitigating the charging is that you scan the multiple frames and let the charge like to dissipate somewhere, and then average those frames. But as you see here, we can sometimes, this was like simulated, but we can sometimes observe the drift of the sample, for example, because of, as I said, we want to imagine something with a nanometer resolution, but for example, there's I don't know, some vibrations from the environment. When you are on very high magnification, you can see in your image that somebody is talking next to the microscope. And also because, I don't know, for some, I don't know, the thermal stuff, the stage can move a bit, or the sample can move, or it was like improperly glued to the stage. So, and glue can be, you know, hardening or something like that. So you can observe this drift. And then if you have like this, this was 16 images, and average those, you will get like this blurry image. So we are using something what is called drift corrected frame averaging. So we want to correct the drift, and yeah, this is what we are aiming to do. Let's go to the example. Frame averaging. Yeah. Let's load. I will show you the intermediate frames just over here, and you can see that they are like quite noisy because I use the small dwell time. So if you zoom in on, how do you zoom on my camera? Which to zoom? Yeah. So it's, you see, it's quite noisy. So yeah, and to be able to distinguish the movement of the images or shift between images, we are using something called registration to align the images to each other. There are like so many ways how to do it. I will present one of those. Anybody familiar with the convolution? So I will use two-dimensional convolution in here. So imagine that if I have like one image and the second one, and the convolution, what it does is like it moves those images with respect to each other or matrices, and then it's multiplying those, and the sum of the multiplication is the value on this position. And if I have like well-aligned images, I got maximum convolution. So this is one of the easiest methods we are using something, because there can be like cross correlation, correlation coefficient, and stuff like that. But let's use this one. This is represented in OpenCV with this filter 2D function. So I will just make a convolution of those two images. This is how it looks like. So when those images met in the middle, it produces highest value. Let's see how it looks like if you compare, for example, so the blue one is represented convolution between first and second image, and the red one is convolution between first and the last image. So we see that the distance between those is like the distance between second and the last image, what it traveled like in pixels. Yeah, and we can plot the shifts. We will just search for the maximum value and say, subtract the center value or the center pixel of it, and then we will get the shift of the images. I know it might be quite because we saw that the image was going to the top right corner, but now why is the y-axis going down? Any idea? Yeah, because we are used for example from some graphs, and that we have like origin in the bottom left corner, but in a domain like when you are doing something with the matrices in computers, the top left corner is the origin. So this is why we are seeing that the y-axis is actually decreasing because the image is going upward. And then I want to align those images, use these values to align those. What I need to do is to construct this transformation matrix. It is actually 3 by 4, right? Yeah. But here is like 3 by 3 matrix where you can incorporate the translation of the matrix. This is what we are using. You can also incorporate the rotation of the matrix, I believe the shear and scaling. So we are just using the translation and use this method board affine, which performs affine transformation of the matrix. And then with each of these aligned images, I will add it to the matrix where I'm storing those registered images, and then I get the result like this. Why do you think we have like these blackish corners or borders?
Because the other image was 0 there.
Mm-hmm. Yeah.
We shifted it.
Yeah, yeah, exactly. So it doesn't produce like nicest result. So what we can do is to have like as well a mask, and just create mask of just once, and also shift this one and edit it to the special variable for it, and then not divide all the values by, I don't know, 16, since we have 16 images, but align it just with the number of frames that number of times or pixels it was actually present in our field of view, and then we will get images with this without the black border. But if we would zoom out into this image, so I believe that you agree that if I compare this one and this one, its signal to noise ratio is way more better. And as I said, if we are going to this top, we see that the image is like more noisy there because we saw those pixels just, for example, once on the border. Yeah, so I believe that was it. Questions?
Did you encounter a problem with this for periodic?
Yeah, exactly. That can happen. Exactly, that can happen. Either you can set some restriction, like how much of the drift you can expect, or make it somehow smarter. But you can also use this phenomena for something called autocorrelation, that you would use the same image for its convolution, and then you can, for example, see some periodicity in the images because you will have like a more local maximas than just one.
Are there any more questions? Hands up. Yeah. Go.
When you program the autofocus, how much or like the first example when you have many images and you search for the most focused one, how much of a problem is distraction of samples with so much electrons from multiple images?
Sorry, once again. Sorry.
When
I was doing the focus,
you have to like produce many images, and you were saying that like the sample is destroyed when you shoot electrons at it for a longer time. So how much of a problem is it that you like have to shoot electrons at it multiple times?
That's for example, that could be a problem. What we are using, sometimes using for these those like prone or sample which are prone to the beam damage, that we usually perform the focus on some different area which then we will be scanning. That's one way. Then my colleagues are, for example, developing the method which will find the optimal place which has enough content to focus on, but it wouldn't destroy your area of interest. So, did I answer the question?
Yes.
Yeah.
Do we have any more questions? Good, thank you very much. Big hand for Lukáš.